we can have several aromatic rings fused together to get bigger aromatic systems. Look at naphthalene, which is just two benzenes attached to each other. If I go around the perimeter of the molecule, I have an uninterrupted system of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 p orbitals all the way around, and I have 2, 4, 6, 8, 10 pi electrons. 10 is 4n plus 2, where n equals 2 this time. So 10 is a magic aromatic number. 2, 4, 6, 8, 10, 12, 14 is an aromatic number. We can keep going. All of these are aromatic in that, we can trace all the way around them to get large rings of aromatic, unbroken rings of p orbitals. The Pogel book called them like a racetrack, where it has to be a cycle where you can go around and around and around unbroken, never passing through any sp3 hybridized carbons. All of these have several resonance structures. Naphthalene has 3, where I can shift the bonds in one of the rings, and then I can shift the bonds in the other ring. But what that gives us in each case is each of those bonds being just like benzene, where it's halfway between a double bond and a single bond. Where naphthalene has 10 pi electrons around its perimeter, this is a nice view of that unbroken racetrack of p orbitals, where the electrons are all evenly distributed throughout them. Heterocyclic analogs of naphthalene are important biologically. Take a look at all of these compounds that have 2 aromatic rings fused together, right? In most cases, one is a benzene and another is a nitrogen containing, like pyrrole, or in this case, tryptophan has a 6-membered benzene ring with a pyrrole type ring attached, and then some other stuff, some amino acid type group there. But the lone pair of that nitrogen is part of the aromatic system. So look at adenine right here, where tryptophan's lone pair was part of it. Adenine is like a pyrimidine, where lone pairs are, where the nitrogens are double bonded, and those lone pairs do not participate. Same with that double bonded nitrogen. But there is a single bonded nitrogen that has a lone pair that does participate. So we've got 2 rings with 6 pi electrons in each, or if I counted all the way around, I'd have 10 pi electrons in it, which makes it aromatic as well. Same thing right here with guanine. 2, 4, 6, 8, 10, going all the way around it that way. Several important biological molecules have that same sort of structure. If you're interested in looking something up, take a look at guanine right here, and then go on Google and look at the structure of caffeine, right? Important molecule to many of us, and you'll see how similar those are. It's a very important, very common pattern that's seen quite a bit in biological systems. But like I said, you definitely should be able to pick out which lone pairs are part of the aromatic system, which lone pairs are in the plane of the molecule and not part of the aromatic system. Okay? The ones that are part of the aromatic system are perpendicular to the molecule, just like all of the other p orbitals.